So we would like to compute the volume of this ellipsoid. And the idea is that we're going to perform a change of variable, and we're going to also take into consideration that the volume of the ball of radius r is 4 pi cubed. I'm sorry, 4 pi r cubed over 3. And we computed this in two different ways in previous videos. Now, let's talk a little about the change of variable. And usually our notation for, let's say, a triple integral, let's work with triple integral since we have a triple integral at hand here, is something like this. And if we have it in Cartesian coordinates, it might also be a good idea to denote it like this, just to emphasize that it is in terms of Cartesian coordinates. So this, in some sense, plays the role of dv for us. But in any case, the question is, what happens if we introduce a new set of coordinates for the domain u? So x is expressed in terms of UVW, same for y, and same for z. Then the question is, what is the way to compute the same integral in terms of UVW? And basically what happens is that we will first need to describe u in terms of the new variable. So let me just denote it by u prime and say that this is the description of u in terms of UVW. And here the understanding usually is that it's going to have a simpler description. Then f needs to be expressed in terms of the new variable. So we're going to replace x, y, and z by their expressions in terms of the new variables. And let's say that as differential, we put here du dv dw. Again, this does not imply a triple iterated integral. Rather, it emphasizes the fact that we're integrating with respect to u, v, and w. And then there is another component which is needed, which is the absolute value of a certain determinant, the Jacobian determinant, which is denoted this way. Oops, see? We put the absolute value because depending on what order we take the variables, depending on the order in which we take the variables, we may get a negative sign, and we don't want the integral to depend on that negative sign. And this determinant is a determinant of partial derivatives, which pretty much gives an expression of the infinitesimal volume of a UVW box in terms of the of those derivatives. So on each row of this determinant, take the partial derivatives of one of the variables. And we should note here that this formula obviously holds in any number of variables. Okay, so with this preparation, let's perform our change of variable here, which is pretty simple. So we said that our goal is to make this look like a ball. So we will introduce x to be equal to AU, y to be equal to BV, and z to be equal to CW. We said that ABC are all greater than 0. And if we take our the description of the ellipsoid, the boundary, for example, is x squared over a squared plus y squared over b squared plus z squared over c squared equals 1. So we look at the boundary. This is a usual method for determining the new domain. The understanding is that the boundary of the old domain will map onto the boundary of the new domain, or its description with respect to the new variables. And this will give us AU squared over A squared plus BV squared over B squared plus CW squared over C squared is equal to 1, which will be U squared plus V squared plus W squared equals 1. That tells us that the description of our domain in the new coordinates UVW is simply the unit ball, because its boundary is the unit sphere. So if we started with the initial integral, which would have been a volume integral over U, then now we can turn this into an integral over U prime of, again, the function 1. And let me put dv here and ask what the Jacobian is. And here the Jacobian, of course, is going to be very, very simple. So the Jacobian of x, y, z. So this partial notation is, I forgot to say that it's classical for the Jacobian. Obviously, it's implied by the fact that all the first order partial derivatives show up here. But in our case, if we look at the expressions that we have, we will see that the partials of x with respect to UVW are respectively A0, 0. Of y, there will be 0, B0. And of z, there will be 0, 0, C. And this determinant is simply ABC. So what we get here is ABC. And we can pull this ABC out of the integral. And now we know that we have the integral of the function 1 over the unit ball in UVW coordinates. And this is where we use our assumption that we have already done this integral in a separate video. And we know that this will be simply 4 pi 1 cubed over 3. Remember, we said it's the unit pole. We found it right here. So the whole thing will be 4 pi ABC divided by 3. And that's it. Thanks for watching.